back. 4.47. Let's see, 4.47. Let's see if this is a difficult one. 4.47. I'm going to start with this one just because somebody brought it up, and I'm curious to see what it was. Am I missing that? 4.47. Oops. Oh, 4.27. Okay. 4.27. Here we go. Okay. Patient named Diana was diagnosed with fibromyalgia, a long-term syndrome, blah, blah, blah. Being a skeptic, Diana didn't initially believe that antidepressants, this is a thought problem, I think, rather than a numerical problem, but it's good. It's timely because we're just talking about type 1 and type 2 errors. Being the skeptic that she is, Diana didn't initially believe that antidepressants would help her symptoms. However, after a couple of months being on the medication, she decides that the antidepressants are working because she feels her symptoms are in fact getting better. Diana's kind of a sample size of 1, right? She only knows her own result, that her symptoms improved. Okay, what's the hypothesis? Now let's talk about hypothesis testing. It's a good time for this, I think, rather than go into the problems. Maybe it's even better that we take a look at this. Okay, obviously we're going to run a little long on this today, but that's okay, I think. Okay, we want to make sure we're still recording. Okay, let's talk about hypothesis testing. Okay, let's see. Let me get a pencil here. Okay, let's say that we're studying fibromyalgia. Okay, and we're telling people, and we're measuring. I don't know, what can we measure possibly with fibromyalgia? Number of lesions or something like that might be observed on a CAT scan or something like that. Let's say it's a number of lesions or something like that observed with some test. We're going to take a sample of 2 groups, for instance. Okay, and one of those groups, we're going to really get a very, very large sample, and this is normal. This is normals. Okay, in normals, we only see 10 of these kinds of lesions or something like that, or people that have low-level fibromyalgia or are normal. They only have an average of 10, and we got a big enough sample that we think, gee, we sampled thousands and thousands and thousands of people. So we're going to assume that the mean for that population of normal people is 10 lesions or something like that. Now, people with fibromyalgia, isn't it like kind of a combination of lesions and scar tissue or something like that, or whatever it's suspected of being? But at any rate, doesn't matter. I'm making all this stuff up anyway. So we take a sample of, say, n is equal to 36 fibromyalgia patients. Okay, we take that sample of patients, and we say, we find some have 20 lesions, some have 5 lesions, some have 30, some have 40, and so on and so forth. We sample 36 patients. Turns out that the mean of that sample of size 36, those 36 numbers, the mean of them turns out to be 15. Okay, so now we want to know, does that mean that these lesions are really associated with fibromyalgia, or is it just by chance that the type of lesions that we're looking at are present in higher numbers for a sample than they were in the general population? Well, we set up a hypothesis. Okay, actually we set up 2 hypotheses. One hypothesis is called the null hypothesis, and the other one is called the alternative hypothesis. Okay, the null hypothesis says there's no difference between the number of lesions that are sampled from fibromyalgia patients have and the number of lesions that normal people have. There's no difference. So how would I write that? A couple of ways I could write that. I could write that as mu for fibromyalgia is equal to mu for normals, average for the population of fibromyalgia patients equal to the average number of lesions for normal patients. Let me just make sure the chat window's open so I don't miss any questions. Hold on just a second. Okay. And the alternative hypothesis is that there is a difference, right? Does not equal the mu for normal patients. I'm just going to say this is what we call a 2-sided hypothesis. That mu for fibro could be lower, could be higher. In fact, maybe it's significant that it's lower in fibromyalgia patients, or as significant. But so we're just going to say it's different. So this is our null hypothesis, or H null, and this is H alt, or alternative hypothesis. Okay, so now something you'll see written as H with it, 0 with a line through it, H null. Okay, so this is our assumption that there's no difference. So the way hypothesis testing works is that we're going to start with our assumption that there's no difference unless we can say with a certain level of certainty, usually alpha is equal to 0.05. Remember, that's our alpha. In other words, with 95% certainty or 5% chance of being wrong, that's our alpha error, 5% chance of being wrong. We're going to say that there's no difference between the two of them unless we can be this certain that there really is a difference. Okay, so how might I determine what the probability of that case being? Okay, well, what I need to know is I need to know what my range of my sample is, my confidence interval for my sample, right? Well, I got x bar is equal to 15. How do I know what my standard error for a sample size of this big is? Well, there's two ways I might know it. One way is that they tell you for the entire population that it happens to be, I'm going to make up a number. Let me make up a good number that's going to work for us. It's going to be, let's say it's going to be 24 for the entire population. That seems kind of big, but we'll stick with that. Maybe I'll make that small. Let's make it 12. Okay. Let's say standard deviation is 12 for the entire population. And I might make the presumption that, gee, it's the same. I expect the standard deviation to be the same for the fibromyalgia patients. Or maybe somebody else did a study that gave us, very, very big study, gave us a standard deviation for fibromyalgia patients. We don't know, but let's say we know sigma. If we know sigma, then we can calculate what the standard error would be for our sample. Standard error for our sample is going to be sigma over the square root of, in this case, the sample size is 36. It's going to be 12 over 6. It's going to be 2. So my standard error is 2. Okay, so I know that if my mean for my calculation, my x bar for our calculation for mean for fibromyalgia from our sample, if that's more than 2 standard deviations away from my mean for the population, from what I'm comparing it to, I know that there's less than 5% chance that they're from the same population. Okay, what I'm doing basically is I'm kind of using what I know about the 95% confidence interval to predict how far apart these two numbers have to be. Okay, so I'm going to do that. I'm going to do that kind of a little bit different way when I do a hypothesis test. And the way I'm going to do that is I'm going to say that I want to know how many standard deviations that these two groups are apart. So let's see, how am I going to do it? I'm going to say x bar minus the mean. I'm going to look at the difference between these two means over the standard error, over the standard deviation or standard error. How many z-scores apart are these two values? Turns out, let's see, 15 minus 10, and the standard error we just decided was 2 because standard deviation was given to us. Okay, that's going to be equal to 2.5. You have 2.5%, 2.5 standard deviations apart, these two results. Do you guys think that I can be 95% certain that the two populations are different from one another, given that the z-score is 2.5? How many of you would agree with me? I can say that I'm at least 95% certain that the two populations are that far apart. How many of you guys agree? Yeah, I agree too, right? That's really what we've done here. What does that mean? That's another way of saying that is that the chances that we're wrong if we say that they're different is less than 5%, less than our alpha of 0.05%, which is corollary to our 95% confidence, right? So there's less than 5% chance. I can actually go to the Z table and see what percentage, what the probability of getting a difference that big is. Okay, so if I went to the Z table, I could look up a z-score of negative and positive 2.5. If I can't find it. Okay, here we go. A negative 2.5. 2.5 is 0.05, about 5.5, 0.5, about 0.5%, right? Actually, remember, almost like 99% confidence interval. Okay, so that's about half of 1%. So if I look at this, the probability of getting this kind of outcome, remember, I didn't say bigger or smaller. I said it could be either, right? As long as it's not equal to, right? So we have 0.5% here in the bottom tail. But we can't forget about the top tail. So we have 0.5% there. It could have been bigger rather than small. It could have been the opposite way around. So my probability of getting this outcome is not only less than 5%, the alpha that I demanded or the confidence that I demanded before I reject the null hypothesis, but I can actually say that the real probability is equal to 0.01%, 2 times 0.5% for two-sided test. So that's 1%. Okay, so now anytime that my p-value, my probability of being wrong is less than my tolerance for being wrong, alpha, I reject the null hypothesis. Okay, in other words, 0.01 is less than 0.05, so I reject the null hypothesis. What does that mean? That means I say I reject the null hypothesis and I accept the alternative hypothesis that the population mean for fibromyalgia patients for lesions is different than the population for normal patients. Okay, now, had my z-score, let's say that instead of x bar being 15, that x bar was 13, right? Well, 13, that would be a z-score of 1.5. Well, that's less than 1.96. So my possibility of being wrong might be something more like 0.06 or something like that, or double, when you double it, be 0.12, right? So 12% chance of being wrong. It's not less than my tolerable level of being wrong, my alpha error or type 1 error. So I would fail to reject the null hypothesis. Would I say that the two means are equal to each other? No, I would just say that I haven't been successful at proving they're not equal. I failed to reject my null hypothesis. Yeah, so if the z-score, if our alpha acceptable level of error is 0.05, right? If the z-score is less than 1.96 in either direction, we fail to reject the null hypothesis, right? We don't accept null hypothesis, we fail to reject it. If somebody said I want to be 99% certain your alpha acceptable level of error is 1%, then your z-score would have to be bigger than 2.58, just like for the confidence interval. So now let's take a look at that possibility. Here's the possibility. We got a mean of 13. The population we know averages 10. Boy, I think fibromyalgia patients have more lesions than normal people do. Okay, so we run through our whole study. We get down here to a z-score of negative 1.5. Says, oh, wow, there is a difference, but it's not enough for me to reject the null hypothesis. Well, in fact, if behind all this, that the mean for fibromyalgia patients and mean for normals really is different, and you didn't manage to prove it, that's called a type 2 error or a type B error. That's considered a little less sinful than a type 1 error, because failing to reject the null hypothesis just means it's passive. That just means that, we saw a little difference. Maybe we'll do another study with a bigger sample size or something like that. But saying that you reject the null hypothesis is a more definitive result and actually could, cause problems, because then people may use this as a diagnostic tool. Okay, so we don't want that. So alpha errors are usually considered worse than beta errors. For the time being, don't worry about how you calculate what a beta error is. It's a little bit more complicated to understand that than a alpha error. Okay, so that's really where we stand with hypothesis testing. Okay, I don't know how far they're going to get into hypothesis testing. Clearly, they at least mentioned it in this exercise. So let's take a look at this. Now, this is really a thought problem, right? So let's see. Being skeptic that she is, Diana didn't believe these antidepressants would help her, but after a while, she was feeling better and so on and so forth. And she says, gee, these things work. Okay, write the hypothesis in words for Diana's skeptical position when she started to take the antidepressants. Okay, well, she didn't think that these things were going to be effective. In other words, let's see, we have a null hypothesis and an alternative hypothesis, right? Her hypothesis was, hey, these things aren't going to help. In other words, the level of pain is going to be the same whether I take the drug or whether I don't take the drug, right? So that's her null hypothesis. What's our alternative hypothesis? Is that there is a difference in pain if I take these drugs. She started out with the assumption that the null hypothesis is true. That's always the way we start. And unless she has data to prove it with some certainty, she's going to stay there and not reject the null hypothesis that they don't work and accept the alternative that they do work. So what would be a type 1 error in this context? Well, type 1 error is if there's some other change in her condition and the pain diminishes, and she attributes it to the antidepressants, but they didn't do anything, right? So she says, oh, I'm going to reject my null hypothesis. There's no difference between taking the antidepressants and not, and accept my alternative hypothesis that there is a difference. That's a type 1 error. That's an alpha error, right? What about a type 2 error? Well, let's say that she takes them and they do help, but something else is going on that she doesn't notice the amount that they help, or that something else that her pain would have been increased had she not taken them, or something like that, and she fails to recognize that they're helping her. That would be a type 2 error. Okay, and so you get an idea of, you can use your own discussion of how you think that these two types of errors would affect the patient. Okay, so but it's kind of like an offbeat problem, right? It's not really. She's a sample of one. We don't really talk about these kinds of things in that sense. How about let's try a couple of these examples. Let's try a couple of actual examples here and so on. I'm going to try one from here. Anybody got a particular one that they're interested in? Okay, should I pick one at random? Let's see. Let's take a look at these two. Yes, basically you got two options. You can reject the null hypothesis, or fail to reject it. And once you reject it, you accept the alternative. There are some kinds of studies you can have several alternative hypotheses, but for the most part, we're dealing with just one alternative hypothesis. Okay, let's take a quick look at this. General GSS, both the survey, demographic, up. It's going to see. Okay. Survey conducts in-person interviews. Randomly selected adults. They sampled 1,154 adults. After the average workday, they asked them how many hours you have to relax or pursue activities that you enjoy. For New Yorkers, that's like none, right? That's -3 hours for New Yorkers. A 95% confidence interval from the GSS surveys is they have where are these people living? They have 3 to 4 hours to do stuff every day before they fall asleep, before they become unconscious, to do stuff that they enjoy. So 3.53 to 3.83 hours. Okay. The 95% confidence interval for the number of hours of free time they have per day is 3.53 to 3.83. Interpret the interval in the context of the data. Okay, so in terms of the data, basically what this says is that the mean was somewhere between the mean from their study was somewhere between 3.53 and 3.83. Actually, it's going to be right in the middle between those two. Is the mean that they found in their study. But the range that they say 95% of the results were likely to be in is going to be between 3.53 and 3.83, or actually the real mean for everybody in the population. What does a 95% confidence interval mean in this context? It means that they're 95% sure that the real number of hours of free time for the population is between 3.5 and 3.8 hours. Suppose the researchers think a 90% confidence interval will be more appropriate for this interval. Will this new interval be larger or smaller than the 95% confidence interval? What do you guys think? Would a 90% confidence interval for the number of free hours for this population be smaller or larger? Right. It would be smaller. It would be narrower because they're willing to accept more chance of being wrong to give them a smaller range. In other words, they would use 1.96, 1.64 for Z instead of 1.96. Well, this new interval be then the 95% confidence. Assume standard deviation. Okay, yeah, you got to assume standard deviation stays the same. Okay, width of a confidence interval, we calculate 95% confidence interval for runners based on a sample of 100. Could we decrease the width of this interval without losing confidence? Could we decrease the width of this? Well, we kind of answered that question before. How would you decrease the width of a confidence interval without losing confidence? Okay, we'd increase the sample size, exactly. So instead of Z changing, Z would still be for a 99% confidence interval would be 2.58. Instead of Z changing, the sample size would change, and that would mean the standard error would be smaller. Standard error smaller times the same Z, it's going to be a smaller margin of error, so it'd be a narrower range. Yeah, okay, let's see. I want to get a real problem here. Okay, these are a lot of these are kind of thought problems. I want to do a calculation here somewhere. Let's see. $11. Okay, let's try this one. Okay, the nutrition label on a bag of potato chips says that a 1 ounce, 28 gram serving of potato chips has 130 calories and contains 10 grams of fat. That's what the manufacturer makes. They lie on this stuff like rugs, I'm sure of it. With 3 grams of saturated fat. There was an old Seinfeld episode where there was a store selling a fat-free yogurt that tasted amazing, and they kept going back to the place because they couldn't believe that this was just so good, this fat-free yogurt. And then as the episode went on, everybody was gaining weight. Exactly, it's fat-free. Okay, so at any rate, so you can imagine, I'm sure the nutrition labeling on some of these on some of this packaging it might be a little optimistic, but at any rate, that's maybe one day that's a good study to do, right? If you guys can find a colorimeter, you could test the manufacturer that you suspect or something like that as a kind of a project. But at any rate, so 130 calories contains 10 grams of fat and 3 grams saturated fat. A random sample of 35 bags yielded a sample of 134 calories with a standard deviation of 17 calories. Is there evidence that the nutrition label does not provide an accurate measure of calories in the bag of potato chips? We have verified the independent sample size and skew conditions are satisfied. Okay, so let's take a look at this. How are we going to solve this problem? Okay, let me get a piece of notepad. Okay, Okay, so let's see what we have here. We have the manufacturer is claiming that that the number of calories is 130. So I'm going to say that he claims that the population mean for the calories in these bags is 130 calories. That's what the manufacturer claims. The manufacturer is saying that that's the true average for the entire population of all his bags of potato chips that he makes. So I'm going to use that as mu. I have to take a sample because I can't check every potato chip bag. I'd wind up heating half of them, as I tried to work with them. But I'm going to take a sample. X bar. In our case, we're going to wind up with X bar, not mu, because we're going to take a sample. So X bar for us is 134 calories. Our sample size happens to be 35. We tested 35 bags. Okay, so now let's see if I got any. What other piece of information do I need here? Okay, there's a standard deviation for our sample of 17 calories. Okay, our standard deviation for our sample is 17 calories. Notice that that is not the standard error. That's the standard deviation for the 35 potato chip bags that we measured. Okay, so we don't know what sigma is. If we knew what sigma is, we would just simply use that to calculate the standard error. Right? It's going to be equal to sigma over the square root of n. Okay, if we knew what sigma was for all the entire population, in other words, if he gave us on the label bag that the standard deviation for all the bags is such and such, that's a variability, but they're not required to give you that information, are they? Come to think of it, now that you know that, when you look at that label, they're not telling you, they're telling you it's 130 calories. They're not telling you whether that really means that it could be between 125 and 135, or whether it could be between 50 and 300, right? They're not telling you that information. They're just giving you the average, right? So we don't know that. So since we don't know that, we have to assume that our sample standard deviation will approximate the population standard deviation. When you have a large sample, that's perfectly okay. When you have a small sample, and I'm going to do this kind of twice, because I'm going to show you what we need to do if it's a smaller sample. And what do we mean by a large sample? Large sample n is bigger than 30. N is greater than 30 is our large sample. Okay, so, or 30. Let's say n is equal to or bigger than 30. Okay, so in this case, we have a big enough sample for me to just assume that this is true for our purposes. Not really true, is it? I mean, we're introducing a little bit of error, but not much because it's a pretty big sample. Okay, so that's the rule that we're going to use. We either need to know sigma, or we have to have a sample size bigger than 30 if we want to use the standard deviation for the sample. Okay, so I'm going to go ahead and solve this now. So what's my standard error equal to? Standard error is going to be equal to, I don't know that, so I got to use 17 over the square root of the sample size, which is 35. I'm going to change this to 36. Okay, standard error is equal to 7. I'm going to leave it 35. Let's do it the hard way. Okay, I'm taking too many shortcuts here. Okay, so let's calculate that. So let's see. Get my calculator out, and first I'm going to do the square root of 35. Square root of 35 is 5.9. And I'm going to divide that into 17. Okay, it comes out to 2.87. So I'm gonna leave that at 2.87. 2.87 is our standard error. Okay, everybody got with me there, right? 2.87. Okay, so now I am gonna. There's a couple of ways I could look at this. One way is I could predict what my confidence interval here is. That's kind of a cheat. If first of all, let's do that. Let's do our confidence interval anyway. So our confidence interval for the true mean for the population, this 130, what we think this 130 is, the true mean is going to be the x bar plus or minus 1.96. I'm using 1.96 here because my sample size is big, or I know the standard deviation. We'll get to that in a second. Times the standard error, which is 2.87. Okay, so what is that? That's going to be 134 plus or minus 1.96 times 2.87. Okay, let's go back to our calculator. I'm sorry, I closed it. So I'm not going to see if I left it open. I could use the actual 2.87 times 1.96. I'm going to store that because that's actually my margin of error. So I'm going to put that into memory. Oh, wow. 1.96 times 2.58. Okay, and I'm going to put that into memory. Okay, so now I'm going to take 134 minus my margin of error is equal to 128.94. Yep, 128.94. And my upper range is going to be, where'd that calculator go? My upper range is going to be, going to clear that, is going to be 134 plus, it's going to be 139.05, 130.05, I think it was. Doesn't matter that much on the upper range. Okay, so now I'm 95% certain that the true mean is between these two numbers, right? So now that means, you see, well, the owner claims, the manufacturer claims it's 130. Well, that's within my range, right? It looks like it could be 130, right? Could be 130. That, our sample certainly doesn't seem to disprove that, does it? Using the confidence interval. The way we would normally do this in statistics is not really use the confidence interval, because confidence interval is kind of a cheat, because it's really intended to be used around the actual population mean, right? Because we don't know that, 134, the real distribution of the sample means is really around the actual population mean. But this is a good way to look at it if we know what the true population mean is, or what's the claimed population mean. And we can look at it that way. A better way to do this is to set up our hypothesis test. Okay, what would our hypothesis test be? The hypothesis test would be the mean that the manufacturer claims is equal to the actual mean of the calories in these things. In other words, that the mean that we calculate is equal to 130. That's our null hypothesis. H null is mu is truly equal to 130. And what's our alternative hypothesis? Well, our alternative hypothesis is mu is not equal to 130. Okay, in other words, that it could be more or it could be less. That's two-sided hypothesis. I'm going to stick to that for now. Okay, so mu is not equal to 130. Null hypothesis, mu is equal to 130, or mu is equal to, you could also look at it as mu is equal to mu, or mu that the owner says claims is not equal to the mu that we claim. Okay, so you could either look at it this way, right? Or you could look at it this way, since we know the manufacturer is claiming 230. Either way is a good way to state it. Okay, so now I'm going to go and do this test now. And how do I do this test? Well, I calculate a z-score, right, for the number of standard deviations difference between what we think the mean is and what the manufacturer thinks the mean is. X bar minus mu over the standard error. Okay, and what is that equal to? That's equal to 134 minus 130 over the standard error, which we calculated to be 2.87, is equal to 4 over 2.87. Okay, 4 over 2.87 is equal to one. I'm going to call it 1.4. A z-score of 1.4. So is z-score of 1.4? Are those far enough apart in standard deviations for you to reject the null hypothesis with 95% confidence, or in other words, less than 5% chance of being wrong? No, you can't reject the null hypothesis. What's the probability that the mean that you would be wrong if you rejected the null hypothesis? Well, you can actually go to the z-table and figure that out. Z for 1.4. Okay, I'm going to do it on the negative side first. 1.40, 8% in the left tail. And since we got to double that for a two-sided hypothesis, 16% total, 8%, 8%, you got 16% chance of being wrong. So your p-value that corresponds to a z-score, two-sided z-score, your p-value is 0.16, right? That's p. And p is greater than alpha, which is 0.05, your acceptable level of chance of error, of making a type 1 error, right? So since p is not less than alpha, p is actually greater than alpha, we fail to reject the null hypothesis, right? It is possible that there's only 130 calories average in the population of all the bags that he manufactured, even though the 35 we sampled came out with an average of 34. Does that mean that he isn't cheating a little bit on the nutritional label? Well, he could be cheating, but our sample wasn't able to demonstrate it with 95% certainty. In fact, we demonstrated it with 84% certainty, but that's not enough for us. We want 95% certainty. We want less than 5% chance of being wrong if we accuse this guy of, for the FBI, we want to be the FDA, not the FBI. I don't think the FBI investigates potato chips. They may eat them, but they don't investigate them. The 5% chance of being wrong, the FDA might use that criteria before they would ask him to, change his labeling or something like that. Okay, maybe they might even use 99%. Who knows? Okay, so that's the way we would do this. Now, what happens if you don't have a sample size of 35? So now we're getting into territory I'm not so sure how far we're going to go on the test with this. we're getting into an area here where if we're dealing with a population, if we're dealing with a sample size that's less than 35, less than 30, and we don't know the population standard deviation, well, that sample is so small. I'm gonna change this to n is equal to 25. That sample is so small now that I can't dependably rely on the standard deviation to really approximate the population standard deviation, sigma, right? So since the only thing I know is the sample standard deviation, and I'm forced to use it, I have to make an accommodation for it. When you get sample size of 25, you have, instead of a z distribution, you have a new distribution called a t distribution, and you have a different distribution for every sample size. Okay, that's based on the sample size itself. So now a sample size of 25, the only difference that would occur here is, since I'm forced to use the standard deviation of the sample, the main difference here is I'm going to accommodate that extra uncertainty by, instead of using 1.96, by using a larger number, 1.96 here, or instead of using and where my z-score is concerned, I would use the t-score as the point where I would reject the null hypothesis. That's called the critical value of t. Okay. Instead of using the z-score, I use the t-score. And how do I determine what that t-score is? Well, I would go to a table that has all those values. Okay, I'm going to go to this particular one. You have a couple as well that you have access to. And it's based on the right tail probability or confidence interval, 95% confidence interval. That's 2.5% in each tail, right tail and left tail. So it's this column, 95%. Okay, and I would go and I have a different t-value for 95% confidence for all sorts of different sample sizes up to super large. And when it gets really large, it's just the z-score. So if I get over 30, I just use 1.96. I don't bother with the small differences here. But this is smaller, so this is a sample size of 25. Notice they don't mention the sample size, they notice the degrees of freedom. And degrees of freedom are equal to the sample size minus 1. So we're going to go down to, instead of 25, 24, go across here. And we're going to, instead of using 1.96, we're going to use 2.06. Okay, so I'm going to go back here, and I am going to use, instead of 1.96 for my confidence interval, I'm going to use 2.06. It's going to give me a bigger margin of error and a wider spread to make up for that level of uncertainty from a smaller sample. And when I go to solve my problem here, instead of using z, I'm going to calculate t, and t now is going to be equal to, let's see, this is going to be equal to 1.4. And 1.4, instead of having to be smaller, it used to be that if we're bigger than 1.96, I can reject my null hypothesis because I know that was 5%. But now t, instead of having to be bigger than 1.96, now t has to be bigger than 2.06. It has to exceed that critical value of t that I need to get to less than 5% chance of being wrong. I think we're getting on the borderline of where we would be on the exam. Okay, so guys, let's call it a morning. I'm going to get this converted and posted as quickly as I can. If you have questions, email them to me, or better yet, make sure that you're logged on to Google Plus and so on, and that you have access to the discussion that's going on and the exchanges that Professor Waldron and Professor Rigetti and myself are answering separately. I guess whoever gets to it first. Make sure you have access to that. If you can't get access to it, and for one reason or another, just go ahead and email us with questions. I'm thinking that most of what you're going to see is 30 or greater, because we got really into the t-score just in the last week. Even hypothesis testing was very recent, and t-score is kind of a little tricky, right? Okay, so I think most of the time you're going to, when you take a study, right? Most of the time when you work on a study, Sample size less than 30 is kind of small sample size. I mean, it's not out of the question, not impossible. You might, especially if you're a student, you're doing a survey or something like that. You might want to limit it, but then you're stuck using the t-score instead of using the z-score. So it is nice to get above a sample size of 30. For our purposes this week, it could go either way, Riley, right? So I would be prepared both ways, but I think you're definitely going to see a lot of situations where where you're going to be giving the population standard deviation, where you're going to be using 1.96 or 2.58 or 1.64 for your calculations. But there might be a couple of problems in there, like mentioned, the t-score, right? It's not really all that complicated. It's just a matter of substituting that t-value for the z-score and then going through the same mechanism for the calculations. Okay, so I hope this helped a bit, and good luck on the test. Okay, so kill it tomorrow. Take care, guys. Bye.